Okay, this is lesson 2 in the MBF 3C version B course, Nets, Patterns, and Plans. This is a bit of a lengthy lesson here in terms of the content in the book. But again, this really shouldn't be too much new in terms of the content work that you should have seen for the most part in elementary school. Probably haven't looked at it a lot in high school since then. Building on the idea that geometry is all around us, and seeing and appreciating different types of geometry, geometric shapes in the world around us, and how it has an impact on our daily lives, and a lot of the potential jobs that are out there in your future, especially in the trades and engineering types of jobs that are out there. This type of math and these types of shapes are quite important. So in this lesson, the idea here is that you will learn these 5 different points: creating perspective drawings of 3-dimensional objects. Some of you, if you've taken art classes, maybe you've even come across this concept in some art classes as well. Isometric drawings of 3-dimensional shapes. There is links at the bottom of my web page for this specific course where you can click on, or under the resources page on the web page, where you can click on these isometric graph papers that you will need. Explain the differences between nets, patterns, and plans. Create some nets, patterns, and plans of your own, and convert some measurements between metric and imperial units. Not to jump over that last one too quickly. Something that seems to be quite lacking, unfortunately, in a lot of your math experiences throughout school is converting between metric and imperial. And even though Canada has been an an officially metric country since, I believe it was September 1980, prior to that we were imperial. And obviously our largest trading partner to the south of us, the United States, is still predominantly uses the imperial units. Because of our history of using imperial units, and our largest trading partner still very much engaged in using imperial units, we just can't get away from knowing and having to understand those units of measurement. Still, I would suspect a lot of people in our society here in Canada still use a lot of imperial units on a regular daily basis. We still tend to use a lot of cooking temperatures, cooking measurements that are imperial-based units. A lot of things that kind of have to do with us sort of personally and in the home, our heights, our weights, things like that. We still talk about calories as well, and it's hard to escape. You know, in pretty much all of the trades as well, there's still a very deep usage of the imperial unit. So it's something we just can't escape. Unfortunately, they're a little bit more complex to use than the metric system. Metric system is very nice. It's all based on basically units of 10, multiples, divisors of 10. But we just can't get away from imperial units, so we'll take a look at that. Anyway, on to part A, making drawings that look 3-dimensional, so perspective drawings. And they draw your attention to this first picture right here, which I'm sure we can all imagine some other similar type scenes that you look at. And this idea of perspective comes along with, which you see a little bit just below the picture there, is this idea of a vanishing point, how things just tend to, as they are further away from us, narrow and narrow and narrow down to one particular point in the distance. So then over on the next page, you'll see that they've drawn some lines, just reference lines along the side of the road and right down the middle of the road. So from your perspective, imagine you're standing, or this photograph was taken sort of standing right in the middle of this roadway. It's a relatively straight line going down the median, and then you can see on the shoulders of the road that those lines definitely converge into a point way off in the distance there, kind of below the foothills that are way off in the distance. But it's that idea of that vanishing point where the particular object that you're looking at vanishes into a particular point way off in the distance. Okay. So they're going to take this perspective drawing that we're familiar with. We saw this in the last lesson. And we're going to take one view of that. So remember we did orthographic drawings of these three-dimensional looking shapes here. And one view of the orthographic drawing was this side view here. And you can see that the little depression channel in the middle is missing. We don't have the dotted line there. This is just a straight block side view. And the way it's drawn it here is it's drawn that side view with a vanishing point off into the distance. And if we just follow the lesson along, we can see that what we do is we take the corners, all the intersection points of the straight lines, and here's where you're definitely going to need a ruler again, and you take those and you draw them all the way back to that vanishing point, wherever you choose to put it on your paper. Sometimes it often helps to put your paper sideways in the landscape orientation instead of the normal upright orientation for this. But that's up to you, and it depends how big an object you're trying to draw and the type of perspective that you're hoping to gain out of this. You can certainly control the way it looks. This almost becomes a little bit a mix, certainly a mix of technical skill and an artistic skill by using this idea of a vanishing point in the distance. You can also see in the bottom corner here, the bottom left corner, that again, the assumption is made that this is a transparent plane, because not only is it the sort of the corners up on the leading right edge, so to speak, all go to the vanishing point. We've also put a line out of that bottom left corner, which is going off to the vanishing point as well. Now, this is where I have a little bit, I take a little bit of issue with the way this lesson is shown. Even though we know in the real drawing that those dimensions across the back, if we just scroll back here for a second, that the total width, if we look at the front bottom here, the total width of this actual object, sort of in this three-dimensional rendering view, is 30 centimeters. And we can assume that the bottom of this was drawn to scale at 30 centimeters. They've chosen to draw back, now again, it looks a little bit deceiving here, draw back along these vanishing point lines 30 centimeters. You're definitely going to, and if you just kind of scroll down here a little bit and you'll see my point, you end up getting this very sort of awkward looking stretched representation of this three-dimensional object that you're trying to do. I disagree with that basically, unless there's some particular reason or more of an artistic nature that you're really trying to draw out and stretch out that object. But as the scale kind of diminishes in the distance, if you imagine looking at that picture up above with the roadway, the scale is not going to be proportionate looking at the face to the lines going back to the vanishing point. So I would argue that if you want to keep your object looking a little bit more in perspective and not stretched out in some very obvious manner, that you don't draw your lines going back along your vanishing point lines the exact same scale length that you would use on the face here. Okay, so we see that this is supposed to be 30 centimeters across the bottom of this particular thing. I would not go back 30 centimeters along my vanishing point. Now, do I have an exact answer for what the scale would be to go back here? No. I would just leave it up to, again, now a bit of your artistic judgment based on the distance back of your vanishing point to pick a distance going back along the vanishing point, not 30 centimeters, not that same length, but something a little bit less that's going to keep this three-dimensional rendering a little bit into in a little bit better perspective. Okay. So now we can see here moving along in the lesson that they're trying to, again, create the idea that this is some type of a clear medium that we're using to draw this object in. So now they're putting in these lines that are 10 centimeters below these particular intersection points so that we can eventually get to the point here where we're going to draw in that recessed channel And of course we're going to need those 10 centimeter depressions reference lines, because that's how deep the channel goes. Okay, and again, when we look at this drawing here as it's progressing along, the base of this cube is 30 centimeters across the face of the base, and we look at how deep this is. It looks very, very skewed and a misrepresentation of the original object. So I would certainly caution you about going as deep towards the back as this lesson represents. But anyway, it's an exercise, and the more of these you do, the more you'll have a feel for drawing these vanishing point type perspectives. And again, bottom line is these are a mix of sort of technical skill and artistic interpretation as well, and representation. Okay. So then finally we can see here that what we're going to do is, depending on how you want to leave your final view, do you want to leave it as a clear type object representation, something that you can look through, or do you want it to look more like a solid object? So you would have drawn all of those with a pencil, and draw them lightly, I would strongly suggest there, and so that you can erase all of those vanishing point lines, and then just leave a representation of this object the way you would like it. Sometimes you want to leave it clear, sometimes you want to erase those internal reference lines as well. That would completely depend on you or what the assignment's asking for. Okay, so here we come to this support question, and we're familiar with this object here as well. And the question wants us to draw a perspective drawing of this object using the same scale of 1 to 10, and again remembering that the tunnel underneath is 20 centimeters high. So I'm just going to zoom in a little bit on this. So when doing your perspective drawing of this here, it's going to be up to you what face you choose to do the perspective drawing of. The solution that it shows in the back of the book is it did the face on perspective drawing, looking at it the way it is right here, basically just kind of replicated this drawing here. We could keep this more simple and just do one of the side references, one of the sides from imagine the orthographic drawing, and did the perspective drawing that way. So I'm just going to keep it a little bit simpler here and choose to do that. I'm going to choose to do the back side. So this being the front side here, it's going to be the back side, actually the same way that we did the orthographic drawing here, or when we did our orthographic drawing. I'm going to slide this up.
And just recall our orthographic drawing that we did was a side perspective. And I'm not going to get too carried away with the scale at this point here. And you can see here that if I go with something quite large like this, it's going to be a little bit more difficult to choose a vanishing point on the sheet in this orientation. It's not that it's impossible, it just makes it a little bit more difficult. And so this is going to be my vanishing point right here. Okay, that's going to be my vanishing point right there. Now,
so I'm going to take a pencil and a ruler, and this is going to be very skewed, and you'll see that just because of the size of the base drawing that I have and the perspective that I'm choosing to use. So all of these corners, just draw them back to that point, all the corners that you can see. Like so. Okay, and again, my argument would be that if I was going to use the same scale I did across the bottom here, which would be the depth of this would be a very strange looking object. So I'm really just going to choose to go by eyeball here to turn this into a perspective drawing, and use that as my reference, or as my scale, versus using measurements. Because as soon as you use these horizontal measurements, as soon as I use a horizontal measurement, my vertical measurements aren't going to be to scale. It's going to be really off. What's really important here to do though is to make sure that any of these lines that you're drawing, and you can kind of see it from the ruler here, any of these lines that I'm drawing, this line needs to be perfectly parallel with this line here. So when you've got objects like this that have nice horizontal and vertical lines, it's really important that your horizontal and vertical lines really match up properly in your diagram, and then that keeps this perspective drawing looking much more reasonable when you go to look at it. Okay, so there's the perspective drawing there, pretty straightforward, and I would then go ahead and erase some of these lines here back to that vanishing point, okay, that I put over there. So VP just for vanishing point off in the distance. Okay. If I wanted to, I could include this bottom line right here, or again, because it's not an actual line that you see, if this wasn't a clear object, I could definitely put this in as a dashed line like this, just to show that it's in behind. And then because these lines are going to be in behind as well, I could join this up with a dashed line like that, and then I messed up a little bit here. I wasn't really careful being parallel. I would match up this line down over here. I can see that this line here is a little bit out from this line right here, but ideally this corner should have lined up with that corner right there. Okay, and then I could erase some of those other lines there. So again, this is a combination of both technical and artistic ability to make these types of drawings work. Okay, so that's that one done. Moving on to the next one now, isometric drawings. Now, this is where I referred you to the web page, and there are a few links on my web page, either under the resources, or if you go to the MBF3C page, where you may have got this lesson from. And on that page there, under the buttons, it'll show you a few different, or it gives you a few different link options for downloading isometric paper. Okay, now isometric drawings, they do look a bit like the perspective drawings, but these ones strive to be a little bit less, or a little less on the artistic side, and try to be a little bit more true to technical dimensions, their actual dimensions. Okay, so take a read over this. Nice thing about the isometrics is you end up working with a graph paper, a style of graph paper, and it says dot paper here. Or you could have paper that look like a bunch of triangles as well. It's basically just this dot paper with all the points connected. You use those as your guides to your 3D perspective. Okay, and we use the dots to make sure that we're staying true to our scale. Okay, and as you can see in this picture right here, we can see that if you count the dots starting at the starting point across the bottom, moving down to the right, you can see that there's 1, 2, 3, 4, 5, 6, 7 spaces there, 7 dots. 1, 2, 3, 4, 5, 6, 7. Okay, going down to the right from the starting point, and then if we go up, it's also 1, 2, 3, 4, 5, 6, 7 dots up as well. Okay, so we can see that our upscale and our downscale is being adhered to using this dot paper. It gets a little tricky to use some of this dot paper, and you might have to take a couple of tries at it to get it right. The little dots, play with your brain and play with your eyes a bit until you kind of get used to working with that perspective and those dots. But you can see how this shape is taking better form. And again, it's going to become a judgment call whether you want to make this look as if it's a transparent cube or if it's a solid cube or not. You can see here that part of it was erased to make it look more opaque or solid. And there's a solid isometric representation of that actual three-dimensional shape. And this looks, I think you would admit, much better in terms of scale as opposed to the vanishing point drawing that it did, the vanishing point perspective drawing that it did earlier. But again, I don't think that representation was very good in terms of its choice of scale, the way that it did the lines going backwards. Okay, so hopefully you've got the isometric paper printed out. And again, like I said, there's two different versions of the isometric paper that you could choose to use. In the lesson, they show the dot paper, and that's fine. There is the dot paper, which you see right here, and I'll work with that one. There's also this one here, which is referred to as a graph paper. So it's the same idea. The intersections of all these triangular grids would be the points, and you could use that, or you can just use the dot paper like this in the lesson. Okay. And like I said, this is what I'm going to use here. So when we, you've got hopefully your diagram there as reference, somewhere close by, and I will try and draw this somewhere on here that will stay in the frame. So if I start right about here, this should be safe. Okay, so this will be my starting point right here. And because the block, the shape, is 13 units deep, I need to go back along here. So every one of these little grid spacings is going to represent 1 unit, okay, on our scale drawing here. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's my base because it's 13 units deep. It was 10 across the flat plane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm just going to mark that anyway. And then it had the additional 3 across the back raised section. So I'm going to take my ruler here, and there's my 13 units going backwards. Now, up the back side of the object, it was 10 units upwards. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units up. Okay, put a little dot right there. And then I can fill in this line like that. Okay. And then I need to come 3 units back along the top. 1, 2, 3. So there's going to be another intersection point right there. Okay. And it's up to you how you choose to progress in the development of your image here. If I go across the bottom here now, I'm going to go 2 units. Okay, and this is where it gets a little bit funky with your eyeballs. There was 2 units here across the bottom. Okay, and then it went up 2 units. And then it went across 4 units. 1, 2, 3, 4 units. 1, 2, 3, 4 units. Came back down 2 from that channel. Over another 2. Okay, and then it went up 6 units. 1, 2, 3, 4, 5, 6 units up. Like that. Okay. 1, 2, 3, 4, 5, 6 units up. So that's going to be an important intersection right there because I have my vertical going up here. And this face piece comes across here. Now that should be 8 units. 1, 2, 3, 4, 5, 6, 7, 8. Good. Okay, so I didn't make a mistake on the bottom here. And then I'll have an intersection 1, 2, 3, 4, 5, 6. Here is going to connect back to here, and you should see that your lines are going along these dot planes. Okay, and maybe your printer might just be slightly off, or the paper itself might just be slightly off if they're not lining up perfectly, but use them as a guide. Use them as a guide point. Okay, and then you just keep going. Now this one across along the bottom here, you could draw this one in right now if you want. That's going to show that piece vanishing underneath there. Okay, and then finish drawing these ones here. 1, 2, 3, 4, 5, 6, 7, 8 right there. So that's going to be this edge, which is also going to connect back to this front corner. 1, 2, 4. This goes up 4. 1, 2, 3, 4. Okay, and it's really coming together quite nicely. It's going to be my last important corner on the top. And that basically is the isometric drawing. Now I could draw in some of these dashed ones in behind, but we're just going to leave this as a solid of that particular shape. Okay, isometric drawing of that shape. To scale, using the isometric approach. Which I suspect would look very different than your perspective drawing that we played around with before that. Okay, so moving on. Reminds us of the orthographic drawing that we did of that shape, the perspective drawing, and now you just did the isometric drawing. Okay, and this one here, just a bit different. Than the perspective, but better scale. On to part B, nets, patterns, and how to construct three-dimensional objects. I suspect, again, this you've probably done in elementary school, playing with nets and taking different types of folded objects apart. I'm sure you would have played around with this either in art or math or some combination thereof on how to fold up a flat piece of paper or two-dimensional piece of paper and create three-dimensional shapes out of it. So here you can see a pretty classic example of just rolling up a piece of paper, turning it around, turning it into a nice cylinder or into a tube. If you cap the ends of it, it'll be a cylinder. Leave it open, it's going to be a tube. Also ties in the connection between the formulas that we use for the two and three-dimensional geometry of these shapes. Okay, and here we can see that it's being pointed out that the distance around the tube, or the distance around the circle of the tube, is exactly the same as the original length of the edge of the top of the piece of paper that we just rolled around onto itself. So the height of the tube is the height of the paper, that didn't change, but the distance around that circle, which is something that's very difficult for us to measure normally, a circular measurement, but when we lay it out flat, it's just a nice straight edge, and that's very easy to measure. So here we see the circumference of the circle being pi times d. Now, support question, it says to create a net that could be used to construct the following can. Okay, basically all it wants you to do is to calculate the circumference, okay, given that diameter of this can. So this was if you were designing some type of a can shape, and it needed to be 7 centimeters across and 10 centimeters high. You need to create a net that would do that. So going back to the formula, C equals pi d, okay, the circumference is going to be the same as the width of the paper, because that's the distance around the top of that tube, right? Okay, so it's giving us this dimension right here as being 7 centimeters is the diameter of that. Okay. And it's telling us that this is 10 centimeters high, overall high. Okay, so when we open up this, if we cut along here, just like it showed in the diagram previously, if we cut along there and open this up flat, all we would have, move this out of the way, all we would have would be a flat piece of paper like this, okay, where the height is still the same. There's the 10 centimeter height, but now this is the opened up edge of that tube, of that cylinder, and that equals the C value across here, which we have to calculate from this formula. C equals pi times the D value, which in this case is 7. So you take your calculator and you type in 7 times pi, if you have a pi button, or 3.14, and this comes out to basically 22, 21.99. But if we just round that off, it's essentially 22 centimeters. And so if you were going to create a net, you could take a piece of paper and you could measure it out with your ruler, 10 centimeters in one direction and 22 centimeters in another direction. Or if you were making a can, you would probably have to cut this out of a thin piece of metal, and then that would be bent around to create the can. Okay, so relatively straightforward, drawing on some geometry that you've probably done since hopefully grade 8, certainly grade 9 and grade 10. Alright, so patterns, like a net, a pattern's a two-dimensional diagram that could be folded into a three-dimensional object. Again, like I said, I would hope and expect that you've certainly done a number of this type of manipulative work back in elementary school. We see the little tabs here on this triangular prism shape, because those little tabs are going to allow you to either glue it or tape it more securely together by having those little tabs available to you from the construction material. Okay, typically paper, cardboard, or something like that. All right, so create a pattern that can be used to construct the following rectangular prism. Okay, please be sure to include exactly one tab for every pair of edges that must be fastened together. Okay, so it means you need to have one tab available for all of those. Now there's certainly a number of answers that you could do here, how you choose to lay this out. All I want to see is that you have tabs there that would be available for attaching with glue on that. And I'm just going to show you here's a box right here, very similar type of a box, right? That was that is part of your question to do right there. Now this has an opening lid. Okay, this also could be a fastening piece right here. If I wanted to fasten this together, I would just have to put an adhesive along here, put this together, hold that together, and then that would glue together. As well, these tabs right here, a little bit of adhesive on there would attach to that surface there as well. Okay, so this shouldn't be anything too particularly new or strange to you. And you see when you look inside here that there's this tab right here on this box that has been glued to this side, and that's what's holding this box together. If I open up the other end of the box, as I'm sure you would expect, it's just completely symmetrical to the other end of the box, and now I can see through there. And here we can see that edge. If we look carefully along here, you can see that that's where this was folded up. So if I open this box all the way up, by releasing this tab right here, it would completely flatten out into a flat piece of cardboard. Okay, and that's one way to make that net into a box. Here's another type of a box that again is basically a rectangular prism. Okay, a coffee cylinder box, but it's taken a very different approach to how it's created its rectangular rectangular prism here. And if I open this up, you can see here's the tab edges on this, and here's the tab edges across the top, that when this folds in, it attaches to the sides the way that they fold up right there. So you need to have those tab edges so that you can put the adhesive there and it holds the edges of the paper together, and then these tabs here fold in here, and you can see that the adhesive will go on there to hold all of those edges together to make this a cubic, a rectangular type of a prism structure as well. Okay, tabs on the bottom here as well. You can see it torn those off and where the adhesive was. Okay, so hopefully recycling and taking boxes apart and stuff like that, you should have a good idea of those ideas of nets and tabs that need to be in place to create those three-dimensional boxes. Okay, so I'm not going to spend any much more time on that. Moving along, metric and imperial system of measurement. All right, so like I said at the beginning here, the metric system is what we officially go by in Canada, but the reality is because of our history and because of our largest trading partner just to the south of us, the imperial system is still very much entrenched in everything that we do. Okay, moving on to the last section in the unit here now, the metric and imperial systems of measure. So like I've said already, we can't escape the metric system or the imperial system in Canada. We need to be familiar with both, given both our history and the American trading partner. This unit doesn't really go into an extreme amount of depth about conversions here. This is more of a really kind of a quick cursory overview of doing some conversions. This is stuff that, you know, there's no shortage of resources on the internet that you can look up other videos on doing conversions between metric and imperial. So I'm just going to move along here and assume that you've got a basic operational knowledge, and we'll kind of go through these simple review conversions that this lesson talks about. Okay. You should hopefully have a decent grip on the prefixes and what the base units are in metric measurement. So the meter is the basic standard unit of measurement. When we talk about things like centimeters and millimeters, those are divisions of the basic unit, the meter. So the centimeter, centi being a 100th, milli being 1,000th, and to convert between millimeters and centimeters is not a big challenge. It's usually just a factor of multiplying or dividing by 10. It's only one decimal place difference. When we're talking about meters and centimeters, like we can see in the example here, centi being a factor of 100, now we have to move the decimal place 2 places, either to the right or to the left, depending on which way we're converting. And again, just have a basic idea of what unit is what the unit is you're talking about, either the meter or the centimeter. If you're converting from meters to centimeters, you know, it should be, I think, obvious to you that the amount of centimeters that you're going to have is going to be a larger number of centimeters than the meter measurement that you had to start with. Just like we see in this example, 2.56 meters, I have 256 centimeters is the equivalent here, just by moving the decimal to the right. Okay, converting 32 millimeters to centimeters. What's the smaller unit? That's the question you should be asking yourself. What's the smaller unit? The millimeter is the smaller unit. Therefore, when I convert that to centimeters, the centimeters, it's going to be a smaller number representing that same length. So we see here in the worked out example that 32 millimeters is the same as 3.2 centimeters. Okay, so if you could just use some basic common sense, then that goes a long way as well. Page jumping around on me here. Now, in terms of the imperial system, the imperial system, unfortunately, is not just a simple matter of of switching, by factors of 10 or 100 or 1,000 or something like that, just all essentially multiples of 10. With the imperial system, there's a lot of basically just rote knowledge that you have to have here on converting between the different measurement lengths. When we talk about inches and feet, you have to know that there are 12 inches in 1 foot, and when we go up to a yard, you have to know that it's 3 feet in 1 yard. Okay, and not so much concerned about converting yards to miles here, but some of the basic measurements that we deal with, inches, feet, yards, you should know those factors. Like I said, 3 feet in a yard and 12 inches in a foot. Okay. And just going on a little bit further here, you see that it's 1,760 yards in 1 mile. That's a pretty rare conversion that you would ever need to do. Inches and centimeters, 2.54 centimeters equals 1 inch. Miles to kilometers, roughly 1.6. That comes in handy when you're talking about distances or driving. Yards to meters, it's approximately the same when you look at 1 meter versus 1 yard. I think a lot of people still refer to the sticks that you see in school that you might use for measurement, or teachers use up on the board. They're often still referred to as yardsticks. You also see them a lot in if you know anybody that does sewing or involved in fabrics and things like that, they still talk about yards of fabrics as opposed to meters of fabrics. So it's still a fairly common, another one of these common imperial things that still exist. And then feet to centimeters. Again, most of you have rulers that you use at your desks in school, and you see that the 30 centimeter ruler is roughly equivalent to 12 inches. Okay, it's very close. You can see the conversion right there. Okay, and so it goes through more of these conversions here. And if we just go over to the conversion section right here, again, I'm not going to spend a lot of time on this. It's worked out in the support question answers at the end. There's no shortage of apps that you can get for your phone as well that will do these basic little conversions for you. Moving on to plans here. Often referred to as blueprints if they've been drawn up officially by somebody. They actually are printed out on a typical blue piece of paper. That's more of a historic terminology. I would say they're probably printed out more on white paper now, but you still do actually see them printed out on large blue pieces of paper, and that had to do with the copying process that used to exist for those types of plans. And here we have a very typical type of a layout drawing for a single bedroom apartment. If you look at any type of real estate listings, this would also be, or house plans, very typical type of a drawing that you would see there, in typical types of measurements that are still, for the most part, done in feet. Just about everything done in the construction industry is still done with imperial measurements. Even though, like I said earlier in one of the videos, or segments of the video, that a lot of these measurements will be metricized, they're still really based on imperial measurements. Okay, so it goes through converting these measurements from their imperial values into metric values based on the scale of this drawing. And it wants you to do the same thing in this example here. So you're going to have to use your ruler and follow this through and measure this out and approximately figure out the scale of these drawings here. Onto the key question finally wrapping up this unit. The key questions, these are now the ones that you're going to have to submit. So drawing a perspective drawing and an isometric drawing. So you're going to have to make sure that you print out another one of those isometric dot sheets for this particular drawing here. Perspective drawing as well, you can just use a standard piece of note paper or blank paper if you have that. Don't use the isometric paper, it's probably going to mess you up for doing the perspective drawing. If you have typical graph grid paper, there's also a link for graph grid paper on the website. You could use that if you like as well for doing the perspective drawing. So set up your vanishing point and then work on that. Again, be careful with how far back you go on your perspective lines so that it looks more reasonable. Again, it's kind of a balance of a technical drawing and an artistic drawing. And for the next question here, it wants you to draw a pattern for this triangular prism. If you've ever had a chocolate bar, some chocolate bars come in little encasements like this here. And don't forget the tabs. Imagine if you had to fold this up and make that shape in class and glue the edges together. You need to have the little tabs on the edges of your net or your pattern to be able to do that. Okay. In this question here, you have two different nets for cereal boxes. Wants you to figure out the volume given on the measurements here. Gives you a reminder of the volume being length times width times height. Figure out that volume. You're also going to have to figure out the surface area of each box. So that's going to be the area of all of these faces here. So I would suggest you reproduce those drawings and carefully label the different areas. There is some duplication of areas there, so once you've done one calculation, you can use it again. You don't have to calculate every rectangle. Basically, you only need to calculate 3 of the rectangles because each of the 3 faces is just a duplicate, and once you've done that, you'll need to add all of those areas together. And then it asks you to do a thought question in part C there as to which one of those boxes you would choose based on its volume and surface area. Okay, now there isn't an exact answer to that last question C. It's going to be a matter of coming up with a reasonable answer and giving some justification.